Okay, let's go over 3A-1 models of Earth. Number one, at the right, sketch a graph of the relationship between the latitude of an observer north of the equator and the observed altitude of Polaris above the horizon. So we said in the notes that Polaris is always in the northern sky, and the further north you go on the planet, the higher it gets. The further south you go, the lower it gets, with limitations. If you go further south than the equator, the curve of the Earth blocks Polaris from view, so you can't see it. So as low as you can go is 0 if you're at the equator. As high as you can go is 90, as it would be if you're at the North Pole. So the altitude of Polaris increases as you head northward. So your graph should look like this, where it's a direct relationship. A latitude of 0 gives you an altitude of 0. A latitude of 90 gives you an altitude of 90, and everywhere in between matches up as well. 45 will give you 45, and so on. Number two, how does the altitude of Polaris change as an observer in the northern hemisphere travels due east? Well, we just said that if you go north or south, Polaris goes higher in the sky if you go north, lower in the sky if you go south. Never did I mention east or west. If you go east, it doesn't affect it. It remains the same. Going east or west does not affect the height of Polaris in the sky. That's one way sailors could navigate by it back in the day. If they kept it the same height above the ocean surface, the same altitude in the sky, night after night after night, that meant they were either going east or west, depending on which side of the ship it was on. If it was getting higher in the sky or lower in the sky, then they were putting some part of north or south in there. So speaking of, if you travel south, what's going to happen to the altitude of Polaris? South means going to lower latitudes, so Polaris is going to get lower in the sky. It's going to decrease its altitude. And opposite of that, if you go north, it's going to increase in altitude. All right, what does this change in the observed position of Polaris suggest about the Earth's shape? Well, it was all evidence of the fact that the Earth was what shape? It suggests the Earth is a sphere. The only shape that can really explain how, as we go north and south, its position changes its position either gets further north, or not further north, higher up in the sky if you go north, and lower if you go south, but doesn't change east or west, is the spherical shape. All right. At what location on Earth is Polaris at its minimum altitude? Where is Polaris as low as it can get in your sky and still be visible? I just gave it away a second ago. So if you go all the way to the north, it gets as high as it can be. If you go all the way to the equator, it gets as low as it can be. So along the equator, when you're at 0 degrees north or south, Polaris is 0 degrees above your horizon. So it's going to be due north from you because it is the North Star, so you always have to look north to see it. And it's going to be 0 degrees up. Maximum altitude and what direction to look. Maximum is going to be at the North Pole. It's going to be 90 degrees above your horizon. And you're really not going to look any direction but up. It's going to be directly overhead. So at that point, let's just look up. 3. What is the best evidence now available that Earth is nearly a perfect sphere? So the key here is now available. Back in the day, a couple hundred years ago, the best evidence might have been what Polaris was doing here. But now we have technology on our side. So the best evidence nowadays would be photographs taken of the Earth from far away that show us the shape beyond a reasonable doubt. Now, by carefully measuring the Earth, we do that with lasers, among other things, radio waves, we are able to discern that the Earth is not a perfect sphere, probably because of the fact that it's been spinning since its formation. Materials spun together to form it. It has a bit of a bulge. It's not visible, but there is a bit of a bulge, a measurable bulge. It's called an oblate sphere. So it's nearly perfect. It's only a fraction of a percent out around. Slightly flattened from pole to pole, a little bulgy around the equator, but the bulge is not visible to the naked eye, only measurable. I liken it to if you've ever picked up a basketball, volleyball, soccer ball that's been abused a little bit, maybe kicked against the wall, sat on, etc. They look very spherical, but when you give them a kick or pick them up and swirl them around, they sort of have a little wobble to them. The Earth's kind of like that, but even that is a little too bulgy. All right, for each item listed below, tell which surface layer of the Earth it occurs in or is found. So earthquakes, well, it's quaking of the Earth. So your three spheres are your lithosphere, your hydrosphere, and your atmosphere. So if the Earth is quaking, that's when the rocks are shaken, and that would be the lithosphere. Water vapor, water is a gas, is in the atmosphere. That's the air you're breathing in. With every inhalation and exhalation, you have some water in that air. Mountains are most decidedly rock, so they're lithosphere. Volcanoes, likewise, are rock, so more lithosphere. Wind. Wind is part of the atmosphere. It's an atmospheric condition, so that's the atmosphere. Waterfalls. This one might get you. Might have tricked you. What do you think? Waterfalls, hydrosphere, because it's the water part. Blizzards, atmosphere. Tornadoes, atmosphere. Coal mines, you're digging down into the ground. Lithosphere, the rock layer again. And tides happen in the oceans in the hydrosphere. All right, so using your ESRTs, your Earth Science Reference Tables, determine which two elements make up the greatest percentage by volume of the Earth. Let's see. So give the percentage made up by each. So the troposphere. This is right on the first page of your reference tables. There she is down below. Troposphere, the biggest percentage, and the second biggest percentage, and these are all by volume. So hopefully you wrote down nitrogen at 78%, and for number 2, oxygen at 21%. The hydrosphere, good old H2O. Hydrosphere, there's your numbers. Pretty straightforward. 1% other stuff. So hydrosphere, H2, so twice as much hydrogen, 66%, as there is oxygen, 33%. It's kind of weird. There's actually more oxygen in the water than there is in the air you breathe. Don't try breathing water, though. That won't work out well for you. All right, and in the crust. Oxygen wins by mass and by volume. We want it just by volume. So by volume, and it's a big drop off by volume. So hopefully you have oxygen, and that number's a little different. Go with the 94.04. Fix it. I think they updated the reference tables at some point. I forgot to fix that. All better now. And over here, potassium. I guess potassium lost a little. 1.42 on this version of the reference tables. All right, so that does us for worksheet 3A-1. Thanks for playing along.